And we can think about how the mean and median are going to relate to the density curve. It's a way to start thinking about how would you find a mean or a median of a continuous distribution instead of a discrete distribution. But we've seen before this concept when we looked at it with histograms. If we think it's going to be similar for the smooth curves, if you have a symmetric distribution, the mean and the median are both going to be dead center right in the middle. Okay, so if you have a normal distribution, which the first picture there, A, is it's a bell-shaped curve. If you find the point that's right in the middle there where the peak is in the horizontal direction, then the mean and the median are both going to be equal to that value there, the height that you get there, or the value on the x-axis if you were to label. If it's skewed, we know that they get pulled toward the tail. Okay? But we also know that the median is more resistant than the mean, meaning the median, because it depends on order, it might move a little bit away from the peak, but the mean is going to move closer to the tail because when you're computing the mean, you're using all those high or low values when you actually compute it. Okay? So that's very similar to what we talked about when we looked at histograms in one of our first chapters. Some notation. So we are starting to make this leap toward inferential statistics, and we need different symbols for our statistics versus our parameters, where statistics are values taken from a sample, and parameters are what we call values for the actual population. And so what most books and most people use in statistics, it's a pretty standard notation. When you're talking about the sample, the actual observations, we use x bar for the mean and s for the standard deviation. And when you're talking about a population represented by a density curve, we use mu, the Greek letter mu. It's pronounced mu, like mu, mu. And it's the little, looks like kind of a squiggly u, but that's a lowercase Greek mu. And then sigma, a lowercase Greek sigma, is for the standard deviation, the population standard deviation. So x bar and s are the sample mean and the sample standard deviation, what we call statistics. Mu and sigma are the population mean and the population standard deviation, or what we call parameters. And the normal distribution is extremely well behaved in terms of the parameters. Okay? We can describe with two numbers, if we know it's a normal distribution, we can completely describe what the curve is going to look like. We know we're going to get this bell-shaped curve, and whatever mu is, that's going to be dead center. So if you draw that vertical line down to the axis there, right in the middle that cuts the graph into two symmetric pieces, that value on the axis would be your mean, mu, your population mean. And sigma controls how wide the graph is. Sigma would tell you where you find what in calculus we call the inflection points. You can call them the change of curvature points, where the graph changes from being concave down, curved down in the middle, to concave up out here on the ends, like a bowl opening up. There's this point in the middle where it changes, which is just kind of in the middle there if you're just trying to eyeball it. If you go from mu to mu plus sigma, that'll get you exactly to that point. Okay? If you do mu minus sigma, it would get you exactly to the inflection point on the other side. So sigma, the population standard deviation, very, very precisely controls how wide the graph is. If you know those two numbers, theoretically, you could draw exactly what the graph would look like. Okay? And so if you have a large sigma, depending on the scale you use to draw the picture, you could always draw the same picture if you adjusted your scale, basically. But let's say you had the same scale for these two graphs. If you have a large sigma, it would be very wide, very spread out. And if you had a small sigma, you'd have a skinnier graph. That's going to be a lot taller, though. For both of these, the area under the graph has to be 1. So if you have a wider graph, it has to be shorter. So let's see a bit of a summary here. So a normal distribution is described by a normal density curve, this bell-shaped symmetric curve. Any particular normal distribution, as I said with the previous slide, is completely specified by two numbers. Its mean mu and its standard deviation sigma. The mean of the normal distribution is the center of the symmetric curve. The standard deviation is the distance from the center to the change of curvature points, or the inflection points on either side. And so we can abbreviate a normal distribution since we only need to know those two numbers. We just need to denote this distribution is normal, and it has a certain mean and a certain standard deviation. So we use the notation, a capital N, and then in parentheses, mu comma sigma. And so you would give whatever the values are. Okay? So you have a normal distribution, and then in parentheses, you tell what is the mean and the standard deviation. That's a very compact way to describe a particular normal distribution. So the use here, what we're working our way toward, is we have a normal distribution for a certain variable we're interested in. If we can find the area under that curve between two values, then that would give us the percent, if we did a percent, or the proportion, if we left it as a decimal, of the population that falls between those two values. Okay? To find those precisely, you would have to have the actual formula, which is a complicated exponential formula for that curve, and you would have to be able to do calculus, okay, to compute them. And it's a terrible integral to do. It's a nasty function, and we could do it by numerical methods. But so we're working our way there in statistics. Ultimately, today we have, in this day and age, right, we have calculators and we have computers that can spit these things out in an instant. Okay, and we're going to use our TI-84 to do these. But we still include, because it's useful if you don't have access to a calculator, and we often count in standard deviations, but if you think about it in historical context as well, what if somebody didn't have calculators? How would they do this? Well, we can compute precisely the hard way what the numbers would be for 1 standard deviation, 2 standard deviation, and 3 standard deviations. Whatever mu and sigma are, when you go 1 standard deviation on either side, it turns out the area is going to be, if you round it, it's going to be 68%. If you go 2 standard deviations, it's going to be 95%. If you go 3 standard deviations on a normal distribution, you get almost the entire population. You're all the way out to 99.7%. Okay? So I have some pictures of each of those so you can think about what this looks like. So again, it doesn't matter what mu and sigma are. This, what I'm saying, is always going to be true. If you've got mu in the middle, whatever that number is, and you go a distance of sigma, which is the standard deviation for that particular normal distribution, and you go to mu minus sigma on the other side, which gets you to those inflection points, if you find the area between mu minus sigma and mu plus sigma on the graph, it's going to be 68% if you round it to two decimal places as a decimal, 0.68. Okay? Sometimes it's more useful to know what's in the tails. We're going to do a problem coming up here, and we're going to have to think about the tails. The tails meaning the parts going out on the end of the graph, so it's symmetric. It has 2 tails. So you have 68% in the middle. There's 100% under the curve, so if you subtract, there's 32% left over, and it's symmetric, it gets split. There would be 16% in each tail. Okay? So we know this, given any normal distribution, if you know mu and you know sigma and you want to go exactly 1 standard deviation away from mu, you're going to capture 68% of the data, and you're going to have 16% in each tail, in the upper and lower tails. If you go 2 standard deviations, so you count out mu plus 1 sigma plus 2 sigma, mu minus 1 sigma minus 2 sigma. So if you go 2 standard deviations away, you capture 95% in the middle. That means there's 5% that's not in the middle, and it's split 2.5% into each tail. Okay? And if you go 3 standard deviations, you get almost 100%. Right? It's going to round to 100% if you round to the nearest whole number here, but it's 99.7 if we round to that accuracy. Okay? There's a little bit out there in the tails, but you get almost everything if you go 3 standard deviations. Okay, so it's extremely rare to get a value that's 4 or 5 standard deviations above the mean. You know, if you did, that would be an outlier, right, on a normal distribution. So if you go 3 standard deviations, so you got mu and you count out 1, 2, 3, measuring by sigma, and you go in the other direction, you capture 99.7% in the middle, which leaves you with only 0.3% in the tails, and that's split 0.15% in each tail if you go 99.7. So we call this the 68, 95, 99.7 rule, which could just be memorized, and you could, at least in the cases where you're counting by standard deviations, figure out these percents, these areas which tell you the proportion or the percent of the population that falls in certain range.